In a groundbreaking study published in the Astrophysical Journal, a researcher from the University of Alabama in Huntsville, UAH, part of the University of Alabama system, investigates the critical aspects of a phenomenon known as kinetic Alfvén waves, KAWs. This research aims to shed new light on a long-standing heliophysical mystery. Syed Ayaz, a graduate research assistant at UAH's Center for Space Plasma and Aeronomic Research, CSPAR, explores the potentially significant role of KAWs in heating the solar corona. This study brings us a step closer to understanding why the corona is much hotter than the surface of the Sun. Alfvén waves have been proven for decades to be the best candidates for transporting energy, Ayaz explains. This paper uses a novel approach to model the energetic particles in space plasmas observed by satellites like Viking and Freja, showing how the electromagnetic energy of the waves is converted to heat as the waves interact with particles during their propagation. The research delves into the disrupted electromagnetic fields, the Poynting flux vector, and the power distribution rate of KAWs in the solar atmosphere. The corona, the outermost part of the Sun's atmosphere, extends millions of kilometers into space and is characterized by extraordinarily high temperatures, a mystery that has fascinated astrophysicists for nearly 70 years. Syed is one of our distinguished students starting his research career, says Dr. Gary Zank, CSPAR Director and UAH Space Science Department Aerojet Rocketdyne Chair. His enduring interest in Alfvén waves, cultivated during his studies in Pakistan with his mentor Dr. Imran A. Khan, has led him to investigate these waves on very small scales, known as kinetic scales, in plasma. Kinetic Alfvén waves are prevalent in the plasma universe, resulting from the oscillations of ions and the magnetic field as they move through solar plasma. These waves are generated by movements in the photosphere, the Sun's outer shell that emits visible light. My fundamental interest in these waves began with the launch of the Parker Solar Probe and Solar Orbiter missions, which raised the important question of how the solar corona is heated, says Ayaz. So far, no spacecraft mission has made predictions about these phenomena close to the Sun, especially within the 0 to 10 solar radii range. Our primary focus is to investigate heating by KAWs within this range in the solar corona. The researchers focused on heating and energy exchange facilitated by KAWs. The reason for the significant interest in these waves lies in their ability to transport energy, Ayaz explains. Observational data from numerous spacecraft and theoretical research consistently show that KAWs dissipate as they propagate through space, contributing to the heating of the solar corona. Due to these unique properties, KAWs provide a crucial mechanism for energy transfer, essential for understanding the energy exchange between electromagnetic fields and plasma particles. KAWs operate on small kinetic scales and can support parallel electric and magnetic field fluctuations, enabling energy transfer between the wave field and plasma particles through a phenomenon called Landau damping, Ayaz explains. The current study uses and examines the Landau damping mechanism, which occurs when particles moving parallel to a wave have velocities similar to the wave's phase speed. Landau damping involves the exponential decay of certain waves in plasma over time. When particles interact with the wave, they gain or lose energy. This is called the resonance condition, Ayaz says. This can cause the wave's energy to transfer to the particles or gain energy from them, leading to damping or growth of the particles. Our research found that KAWs dissipate rapidly and transfer their energy entirely to plasma particles in the form of heating. This energy transfer accelerates the particles over longer spatial distances, significantly impacting plasma dynamics. The analytical insights from this study will have practical applications in understanding phenomena in the solar atmosphere, especially highlighting the important role of non-thermal particles in heating processes.